Before I proceed with the discussions on DAC, refer back to this system that I considered. I pointed out that this system is time varying. Did you check it properly? দাঁড়াও, আমি একটু এক্সিট করে আবার ঢুকছি। টাইম ভ্যারিং সত্যি হচ্ছে কি না? হ্যাঁ
স্যার, এটা টাইম
করেছিলে? হ্যাঁ
স্যার, এটা কি টাইম ইনভ্যারিয়েন্ট?
টাইম ইনভেরিয়েন্ট। তাহলে তুমি কি মানে পরে চেক করেছো না তখনই বুঝিয়েছিলে? তাহলে বলনি কেন?
না স্যার, এখন মনে হচ্ছে আসলে স্যার তখন ওই আইটা আর কি আপনি বললেন, তারপরে আর কি একটু তখন বুঝতে পারিনি, এখন মনে হচ্ছে এন এর উপর ডিপেন্ড করবে। এখানে এন কে যদি একটু ল্যাগ করানো হয় তাহলে তো আউটপুট জাস্ট মানে সেই অনুসারেই আর কি চেঞ্জ হবে, মানে টাইম ইনভ্যারিয়েন্টই হওয়া উচিত।
Here, if this coefficient were dependent on n, not on I, if this coefficient were dependent a1 to the power I, if this a1 dependent on n, then only it would have been time variant. But now here it is time invariant. So I'm sorry that I made a mistake. I didn't do the proper homework. So it is not time invariant. The realization requires infinite memory, hence not realizable. That is the actual point. But that this system is time invariant, how to verify that? How to verify that?
Sir, if we put x n instead of x n minus, that means we put x n minus k instead of x n, just like continuous time system.
Okay, you just check this one in this way. Suppose xn is equal to delta n. All right. When xn is equal to delta n, what will be yn? Say it will be some y1n. What will be the expression? In this summation expression, I have replaced x with delta. All right. Now here in this summation, only the term for which I is equal to n, for that term delta n minus I will be 1. For all other values of I, delta n minus I will be 0. So only the term for I equal to n, that term will remain. All right. So what happens to this summation? It becomes y1n equal to a1 to the power n. Because only for I equal to n, this is 1. For other values of I, this is 0. So y1 is equal to a1 to the power n. Now let, in the next example, as a next case, consider xn equal to delta n minus 1. So yn equal, what does yn become? Yn becomes y2n equal to this summation a1 to the power I delta n minus 1 minus I. So this delta n minus 1 minus I, this will be equal to 1 only for I equal to n minus 1 and 0 otherwise, isn't it? So in this summation, only the term for I equal to n minus 1 that will remain, and that delta n minus 1 minus I for I equal to n minus 1, that will be delta 0 equal to 1. So here, because delta n minus 1 minus I will be 1 only for I equal to n minus 1 and 0 otherwise, y2n will become a1 to the power n minus 1. That means y2n is y1 n minus 1. So you have delayed the input by one sample. The output also gets delayed by one sample. In a similar manner, you can, if you consider xn equal to delta n minus 2, you will find that, sorry, this will not be y2n, this will be y3n, equal to a1 to the power n minus 2. That means y1 n minus 2. So if you delay the input sequence by, say, m number of samples, small m, Madras, small m number of samples, then your output also get delayed by small m number of samples. That is the point. So this is a check for time invariance. Therefore, in this case, we have found that the system is time invariant. So just strike out. All right. Strike out these parts. I am sorry. Just delete these things. Only write that the realization requires infinite memory, hence not realizable. And if you wish, you can write this check for time invariance. I want that you write down these steps. Then you will understand how to check the time invariance of LTI systems. So I may give you question in which you may be asked, you may be given some examples, and you may be asked to check whether they are time invariant or not. So be prepared about that. So strike out all these things that you have written earlier. In the other example that I had cited, this case, so this is also a time invariant system. All right. So if you have written it as time varying system, please strike that out. All my other observations remain same, remain intact. Now I am moving on to the practical digital to analog converter. We had considered the ideal interpolator or ideal DAC or ideal discrete time to continuous time converter. Now we are moving on to the practical DAC. I have pointed out the problems that we will face in implementing the ideal interpolator. So that cannot be used. So what does the practical DAC do? A practical DAC, a real life DAC, it uses a zero order hold. It uses a zero order hold for reconstructing the analog signal from its sampled version. All right. That is what a real life ADC does. So there are two operations involved in digital to analog conversion. Input to the DAC are samples, each of which is coded using binary numbers. All right. So that binary coded sample has to be converted. Each of the binary coded samples has to be converted into a decimal number. So that is the first task. That means a decoder must be there. Second is to convert that decimal number, those collection of samples, into an analog signal or a continuous time signal. That is done by this zero order hold. Don't think that inside the DAC there are completely two different subsystems, one for decoding, another for zero order holding. It's not like that. But the DAC as a whole performs these two tasks. For the sake of convenience, I have just segregated them as if there is a decoder followed by a zero order hold. But both decoding and zero order holding, that is intrinsic in the DAC. Now decoder, if you think about the decoder, what does it do? It simply represents the input sample in a different format. So that has no influence on the transfer function or frequency response of the digital to analog converter or the discrete time to continuous time converter. Therefore, the transfer function and consequently the frequency response of discrete time to continuous time converter is simply determined by the transfer function or frequency response of the zero order hold. I have represented the output of the DAC as XRT. XRT. R stands for reconstructed. R stands for reconstructed. All right. So what does a zero order hold do? How does it yield a continuous time signal from the sampled version, it simply holds, the zero order hold simply holds every sample value until the arrival of the next sample. So if that is done, just see here that the sample at t equal to minus 3 tau, this is held by the zero order hold until a new sample arrives at t equal to minus twice tau. Once that new sample arrives, it captures that new sample and holds it until the new sample arrives at t equal to minus tau. So in this way, the output of the DAC, it approximates a continuous time signal in the form of a staircase signal. So this is simply staircase reconstruction of the analog signal that we desire. So x tilde t is the input to the zero order hold, output is xrt. All right. Now this staircase reconstruction, because there are discontinuities at every sampling instant, it indicates the presence of high frequency components, high frequency contaminants in this signal. That will be clear, not be clear to you unless I come up with the frequency response of the zero order hold. So right up to this one, then I'll proceed. That staircase signal that I have drawn, you can easily write down the expression for that staircase signal from your knowledge of signals and systems. TF stands for transfer function. Those who have joined late, please note that I have made certain corrections or amendments to my earlier observations yesterday's. So just make the necessary corrections. Consult your friends and make the necessary corrections. I am sorry for those mistakes. I shouldn't have done it. Let me enlarge it. XRT is the staircase waveform. That is XRT. And HT is whatever I have drawn in with these dots. That is the signal that we desired at the output of the DAC. এইখানে না এইটা একটু গন্ডগোল হয়েছে। এই জায়গাটা এই এক্সটেন্ডেড হবে, এখানে নামবে না। দেখো একটু ভালো করে, এটা এক্সটেন্ডেড হবে হয়ে এইভাবে আসবে, ঠিক আছে? এইভাবে নামবে, কারণ এই ভ্যালুটাকে তো হোল্ড করে রাখবে এই ইনস্ট্যান্ট পর্যন্ত। এই ইনস্ট্যান্টে নেবে এই ভ্যালুটাকে ক্যাপচার করবে, এটা হোল্ড করে রাখবে আবার এই অবধি, এইভাবে এগোবে। এখান থেকে একটু প্রবলেম আছে, ঠিক করে নিও। So correct that mistake there. Have you drawn the figure?
Sir, could you please scroll up?
Yes. Could you follow what I mentioned?
Yes, sir, I've corrected it.
Yes, yes, all right. So that is the equation, the staircase waveform, it can be expressed in this way. So that is the expression for the reconstructed staircase waveform, XRT, summation of x and tau multiplied by the difference of these two steps. N having values of 0, plus minus 1, plus minus 2, etc. How would you proceed further towards determination of the transfer function of this system or the frequency response of the system? Okay. So if you take the Laplace transform of both sides of this equation, what will happen? On the left hand side, you will represent the Laplace transform by capital X subscript R with argument S. What will be the expression if you take the Laplace transform of the right hand side? The Laplace transform operator will operate only on those functions that contain small t. All right. So what will be the Laplace transform of these two difference of those two signals? 1 by S will be there. Then so this will be the expression for the Laplace transform. So if you just keep e to the power minus n tau s inside this bracket, I mean inside this summation, sorry. All right. If you just keep e to the power minus n tau s inside this summation, why we are doing that, you'll understand. What will come out of this summation will be 1 minus e to the power minus s tau divided by s. So within the summation, we have x n tau e to the power minus n tau s, whose Laplace transform is represented by this expression, by this summation. This summation represents a Laplace transform of a certain signal. What is that signal?
Sir, impulse. Impulse.
Yes. Sum of impulses with strength x and tau. All right, Laplace transform of this summation, x n tau into delta t minus n tau. Is it clear? This summation represents the uniformly sampled signal. So this is Laplace transform of x tilde t, that is capital X tilde s. So ultimately in this equation, xr s is equal to whatever is there within first brackets times capital X tilde s. Now if you consider this zero order hold, or you may say the practical DAC, what is the input to the DAC? It is x tilde t. So the Laplace transform of that is x tilde s. What is there at the output of the DAC or the zero order hold? It is small x r t, whose Laplace transform is capital X r s. So what does this represent? Whatever is there within brackets, first brackets, 1 minus e to the power minus tau by s. What does it represent? On the left hand side, you have the Laplace transform of the input. On the right hand side, you have a function of s times the Laplace transform. Sorry, on the left hand side, you have the Laplace transform of the output. On the right hand side, you have a function of s times the Laplace transform of the input. So what is this one?
Transfer function.
It is the transfer function of the zero order hold, or you may say the transfer function of the DAC, practical DAC. So I am writing it in this manner: GHOS equal to 1 minus e to the power minus s tau by s. This is the transfer function of the zero order hold. From this transfer function, you can easily obtain the frequency response. I'll proceed in that direction. But before that, just consider this transfer function of the zero order hold. See here, I have expanded e to the power minus s tau into an infinite series here. So then I have simplified, you get this result. All right, tau minus s tau square by 2 plus s square tau cube by 6, like that. All right. So if you truncate this series, for very small tau, if you truncate this series after the second term and ignore the higher order terms, it becomes tau into 1 minus s tau by 2. This is approximately equal to whatever is there within brackets. This is approximately equal to e to the power minus s tau by 2. All right, for very small tau. Therefore, tau is a multiplying factor, a constant. Once you have decided the sampling frequency, tau is settled, it's constant. What type of a system that this transfer function represent? E to the power minus s tau by 2. What type of a system does this e to the power minus s tau by 2 represent? Okay, let's put it this way. Suppose you have a system with transfer function e to the power minus s into capital L, and the input to the system is, say, small xt. What will be the output? You get my point? Suppose you have a system with transfer function e to the power minus s into capital L. You excite the system by a signal xt. What will be the output?
X of t minus L.
Very good. It will simply be the delayed version of the input by L units. So e to the power minus s tau by 2, it represents the transfer function of a system that is simply a delay element. The delay being half the sampling frequency. All right. Therefore, it is often said that the zero order hold introduces a time delay of approximately half the sampling period, tau by 2. All right. This fact is important when you, in the domain of digital control. Digital controller, they are nothing but discrete time LTI systems. I mean, if they are linear and time invariant controllers, there are other versions also. Non-linear controllers also exist. So in that case also, this delay may be important if you use when you have to use a DAC there, isn't it? The error signal, you are studying control theory, I think. The error signal is processed by, it is sampled and processed by some numerical algorithm, some processor-based system. And accordingly, it generates an output. Now to drive the final control element, this output is to be converted into an analog signal. So there must be a DAC. So that DAC is also a zero order hold. So because that introduces a time delay of half the sampling period, that fact is important in certain cases in control systems. Now come to the frequency response function of zero order hold. Start from the expression for the transfer function. Replace S with j omega. You get this expression. 1 minus e to the power minus j omega tau by j omega. In the numerator, if you take out e to the power minus j omega tau by 2, what remains inside the brackets? I mean, what remains in the numerator? It will be e to the power j omega tau by 2 minus e to the power minus j omega tau by 2. Multiply this difference with e to the power minus j omega tau by 2, you will get the numerator. 1 minus e to the power minus j omega tau. So I have maneuvered this expression in that manner. In the denominator, you have j omega. All right. So the denominator is modified in this way. I have multiplied by 2 divided by 2, and I have brought in a tau term here. All right. Therefore, I have to introduce another tau term there so that the two taus cancel out. From that expression, how can you proceed further? This one is, what does it represent? This is sine omega tau by 2 divided by omega tau by 2. So what type of a function is this one? You have this expression e to the power minus j omega tau by 2. So that is the expression for the frequency response of the practical DAC. So what will be the amplitude response function? The exponential term will have no contribution to the amplitude response. Amplitude response function will simply be tau into magnitude of this term, sine omega tau by 2 divided by omega tau by 2. So that is the expression for the amplitude response of the zero order hold. The phase response function is this one. Argument of sine omega tau by 2 minus omega tau by 2. It will come out as plus minus m pi minus omega tau by 2, m having values of 0, 1, 2, 3, etc. We are interested more in the amplitude response function. How will it look like? First, complete this part. You have written up to equation A or what? এই অবধি লিখেছিলেন না, কোন অবধি বলো তো? অ্যান্সার ফাংশনটা লেখা হয়েছিল?
হ্যাঁ স্যার।
আচ্ছা, এটা লেখো। when you complete up to equation C, please let me know. I'll move on to the next page.
স্যার এখানে অ্যাঙ্গেল সাইন ওমেগা টাউ বাই 2 মাইনাস ওমেগা টাউ বাই 2 হলো কেন অ্যাঙ্গেলটা?
এই যে e to the power minus j omega tau by 2 আছে যে।
হ্যাঁ স্যার, সেটা তো তাহলে তো শুধু মাইনাস ওমেগা টাউ বাই 2 হবে না?
হ্যাঁ তাই তো, এইটার যে আর্গুমেন্ট থাকবে,
আচ্ছা স্যার, এটা কমপ্লেক্স।
সাইন থিটা বাই থিটা, তার যে আর্গুমেন্ট থাকবে তার সঙ্গে এটার আর্গুমেন্টটা যোগ হবে। এটার আর্গুমেন্টটা কি? মাইনাস ওমেগা টাউ বাই 2, ঠিক আছে? এই সাইন ওমেগা টাউ বাই 2 এটার আর্গুমেন্ট তো তোমার দুটো পসিবিলিটি, তাই না?
হ্যাঁ স্যার।
একটা সার্টেন ব্যান্ড অফ ফ্রিকোয়েন্সি জুড়ে এটা তোমার মানে পজিটিভ থাকবে আর একটা হাফ সাইকেলের নেগেটিভ থাকবে।
হ্যাঁ স্যার।
Sir, could you scroll up 1 second?
Yes, sure. Should I scroll up further or this one?
না স্যার, অ্যাঙ্গেলটা একটু দেখতে হবে।
So this is the amplitude response. The frequency response, you can well understand that the frequency response, excluding that e to the power minus j omega tau by 2, if you consider the frequency response, then it is a sinc function. So the magnitude response function is that just the sinc function, but with this negative parts made positive. So I have drawn here in black the amplitude response of the zero order hold or practical ADC. And whatever is drawn in pink, that one is the ideal filter, means ideal DAC, right there, ideal DAC. Magnitude of GI j omega. And black one is magnitude of GHO j omega. So what is the difference of this amplitude response of the zero order hold from that? What is the difference between the amplitude response of the zero order hold and that of the ideal DAC? Just see here, first of all, the zero order hold, because the gain is not zero outside, outside this band, minus omega s by 2 to plus omega s by 2. Outside the band, the gain is not zero. Not only that, it doesn't monotonically decrease to zero. It again rises like that. Therefore, what is the input to the zero order hold? Spectrum of the input. It consists of the baseband spectrum and infinite number of aliases centered at integral multiples of the sampling frequency. So those remnants from those aliases or images, they will be passed through the zero order hold. Remnants, replicas, contributions from the replicas, some portion of the replicas, they will be allowed to pass through. Not only that, the baseband spectrum, that means the spectrum of the original analog signal. So that will also be mutilated to a certain extent. That will also be distorted to a certain extent, because over that span minus omega s by 2 to plus omega s by 2, the gain is not constant. It's changing. Therefore, the spectrum, obviously, that was what was expected or apprehended, you may say. The output will be a distorted version of the signal that you desire at the output. Now, this phase response function, I will not, that is not very important in this case. But this is not the plot of the phase response function. It is not unique. It can be, several other possibilities are also there. For example, it could have been also like that. Say this part, straight line, then it will become 0 from omega s to twice omega s. Again, it will rise linearly. Again, it will become 0. In this way also, it can continue. All right, like that. Or what? Twice pi. Yes, twice pi. Think about what are the other possibilities. These frequencies are omega s, twice omega s, thrice omega s in this direction, minus omega s, minus twice omega s, minus thrice omega s, etc. So that's what I pointed out. The nature of the amplitude response indicates that this practical DAC will allow high frequency components of the sample signal to pass through, digital signal to pass through. Suppose this was the amplitude spectrum of the original analog signal. Original analog signal, suppose the system is like this. We have an analog signal. We are digitizing it using an ADC. So we are getting a uniformly sampled signal. Then it is again converted back into an analog signal using a DAC. This is the situation. A very hypothetical situation. That type of situation cannot arise in practice. You can well understand. But just for the sake of understanding, you have an analog signal that has been digitized to convert it into a uniformly sampled signal. Then and there it is converted into an analog signal again using a DAC. So suppose this was the original analog signal. Now for the given system, what do you expect at the output of the DAC ideally? The analog signal right at the beginning, isn't it? That's what you desire ideally. So if the input signal, analog signal is small xt, at the output of the DAC, you expect small xt. Let's proceed on that premise. Suppose the amplitude spectrum of the analog input is magnitude of xjf. So it's a band limited signal with the bandwidth fm. Say it's uniformly sampled, satisfying that sampling theorem. Fs is greater than twice fm. So whatever I have drawn here are simply this one centered at f equal to 0. That is this baseband spectrum. The spectrum of the original analog signal scaled by fs. Height is fs instead of 1. And those are the different aliases. All right. Or different images. So there are two possibilities. One is the ideal interpolator or ideal DAC whose amplitude response is represented in pink, and the black one, that magnitude of sync function, it represents the amplitude response of the practical DAC, which is written here as staircase reconstructor. That is the amplitude response. So what will be the amplitude spectrum of the output? It will be, if the output is XR, then the amplitude spectrum of the output is magnitude of capital XR JF. It will be the product of magnitude of GHO JF with the amplitude spectrum of X tilde T, the sampled signal. So those infinite number of images, the baseband spectrum together with this infinite number of images, they are to be multiplied with this staircase reconstructor amplitude response. The magnitude of sync function, it is to be multiplied with this infinite number of replications. What will be there? So this is what I have labeled as the magnitude spectrum of the output of the zero order hold. Just see here, because it has a curved nature in the span minus fs by 2 to plus fs by 2, এখানে minus fs by 2 হবে, to plus fs by 2. Therefore, the baseband spectrum is itself has got distorted to a certain extent. Not only that, because the gain is not zero outside fs by 2, minus fs by 2 to plus fs by 2, remnants of these replicas, a portion of these images, they are also present. So whatever I have marked in gray, that represent the spectrum, amplitude spectrum of the output of the zero order hole, magnitude of x or jf. So this baseband spectrum, I have referred to that as partially attenuated baseband spectrum, because it is not similar to that trapezoidal thing, which I assumed as the amplitude spectrum of the analog signal. So this is the problem. The staircase nature, its manifestation in the frequency domain is whatever is shown here. If we had used the ideal interpolator, if it were possible to use the ideal interpolator or ideal DAC, this problem wouldn't have been there. We could have exactly obtained magnitude of xjf at the output. So just write this part. I am referring to the same thing by different names, just to make you acquainted with different possibilities. এখানে দেখো আমি staircase reconstructor বলেছি। কোনো বইয়ে হয়তো এরকম টার্মও আসবে, হয়তো না আসবেই। কাজেই তোমরা যাতে বুঝতে পারো সেটা, so that you understand, I am using here different types of names to describe the same thing. এইখানে দেখো মাইনাস fs/2 হবে, এই যে fs/2 টা নেগেটিভ সাইন আসবে। How can you get rid of these so-called surviving replicas? How can you get rid of them? Now remember, at the output of the DAC, you have an analog signal, a continuous time signal. So how would you get rid of? You are free to add any extra thing. I want to remove those surviving replicas from the spectrum.
Low pass filter.
Yes, we can add one analog low pass filter after the DAC. In fact, that is done. So that is only a partial remedial measure. For a large variety of system, this partial remedial measure is sufficient. But for more sophisticated system, you have to some approach towards complete compensation is to be obtained. When I say partial remedial measure, why do I call it partial? Because by placing a low pass filter, you will be able to block these contributions from the images, all right, these surviving replicas. But you cannot restore back whatever what was attenuated, this baseband spectrum, that you cannot correct using a low pass filter.
Sir, please repeat this thing again.
If you use a low pass filter after the DAC, these surviving replicas, they can be blocked, no doubt. What will be the nature of the amplitude response of the low pass filter? Some constant part here, then it will droop. All right. So those remnants can be blocked. But the fact that because of the non-constant value of this gain of the staircase reconstructor over minus fs by 2 to plus fs by 2, because this was the nature of the amplitude response, the baseband spectrum also got distorted. That's why I have written it as partially attenuated baseband spectrum. So that is also a source of error. Can that be restored if you simply place a low pass filter? That cannot be restored using low pass filtering, isn't it? বুঝতে পেরেছো? এগুলোকে ব্লক করা যাবে, কিন্তু এটা যে ডিস্টর্টেড হয়ে গেল সেই কারেকশনটা তো লো পাস ফিল্টার দিয়ে করতে পারবে না। Anyway, when you complete drawing, I'll proceed. I'll throw light on how to do that. Very simple, but very difficult to implement using analog circuit, if not impossible. বলো ছবিটা হয়ে গেলে। এখানে কিন্তু ম্যাগনিটিউড অফ এক্স আর জে এফ স্কোয়ার্ড নয়, এটা হচ্ছে এফএস বাই 2 এর 2। এই হয়েছে।
Yes, sir.
Zero order hold also distorts baseband spectrum and also allows inclusion of portions of some of the replicas of baseband spectrum, leading to further distortion. All right. Now, within the passband, that means in the span minus fs by 2 to plus fs by 2, or you may say, if you are interested, obviously, for obvious reasons, only positive frequencies, f equal to greater than 0, less than fs by 2. What is the percentage distortion that the zero order hold will introduce? Why it is tau minus this magnitude divided by tau? Because within the passband minus fs by 2 to plus fs by 2, if you had used ideal interpolator, if it were possible to use ideal interpolator, the gain would have been tau. This ideal interpolator, the gain is tau. Gain would have been tau. Now, instead of tau, it is following the amplitude response of the zero order hold. So that's why the percentage distortion is expressed in this way. Tau minus magnitude of GHO JF over F equal to 0 to Fs by 2 divided by tau, expressed as a percentage of tau. I have simply introduced the expression for magnitude of GHO JF. It comes out as 1 minus sine pi f tau divided by pi f tau into 100.
Sir, please scroll up.
এখানে না কোথায়? আরো আগে?
না স্যার, ওখানে
আচ্ছা, ঠিক আছে। লেখা হলে বলো।
Hey guys.
Now overcoming the zero order hold effect. So because the sampling frequency is quite high, sufficiently high rather, low pass post filtering, that means placing an analog filter, as you have pointed out, placing an analog low pass filter after the DAC, it can isolate the baseband spectrum from the remnants of its replications. So only allow the baseband spectrum to pass through, but block the contributions from remnants of the replications, images. Therefore, this low pass filter, it is also known as image rejection filter. The cutoff frequency of this filter is obviously half the sampling frequency. And obviously, it's very similar to anti-aliasing filter in characteristic. That is one part of the story. But the fact that the baseband spectrum is distorted, how can you take into, bring about some remedial measures? All right. So I have tried to illustrate. This was the baseband spectrum that was attenuated, magnitude of X or JF, attenuated baseband spectrum. See that the head is curved, not flat. So at the output of the post low pass filter following the DAC, it will remain almost same. All right. So X naught O, that is the output of the low pass filter following the DAC. Now for certain applications, it will be acceptable. Baseband spectrum, further improvement of the baseband spectrum is not required. But in other applications, as for example, high quality digital audio, this is not allowed. So some remedial measures have to be brought in. So what extra thing can we add here? We are trying to eliminate the distortion of the baseband spectrum produced by the analog, the zero order hold. So what type of system can introduce necessary correction? Suppose there is a system, a certain transfer function, which processes a particular input. So at the output, you have a modified version of the input. Now, if you want to bring back the original signal from this modified version, what type of system theoretically do you propose? So you have a system with transfer function GS. It modifies a certain input signal xt to produce a certain output signal x naught t. So what type of system would you place in cascade so that the output of this second system is xt back again? Huh?
Inverter.
Inverter means?
That means the system which converts the xt to x0, you have to take the inverter of that system that converts x0 to xt.
Inverter, what does it mean? What transfer function will it have? If the original system is GS, the second system, what will be the transfer function?
So 1 by gs.
1 by GS, right. So here also we can do that. I mean, we can theoretically do that. Within the band minus fs by 2 to plus fs by 2, what was the nature of the zero order hold? concave upward characteristic. Sorry, convex upward characteristic. Convex upward characteristic, isn't it? So after the low pass filter, if we introduce another filter, that will have just the inverse characteristic. That means concave upward characteristic in the pass band. And that filter has zero gain outside the pass band. That type of a system. See here. If it is possible, then after the post filter, if we can implement a system with that transfer function, G magnitude of G CR JF, then it will be possible to nullify the distorting effect of the zero order hold within the band minus fs by 2 to plus fs by 2, isn't it? But implementing that type of a system using analog circuitry, that is almost not possible. All right. So what is done is that instead of placing this after the post filter, prior to digital to analog conversion, a discrete time LTI system is placed prior to digital to analog conversion. A discrete time filter is placed before that, which can be made to have almost that type of characteristic. So in this way, compensation can be done to a considerable extent. All right. So write this part. একটু তাড়াতাড়ি লেখো, তোমাদের 12টা থেকে আবার ক্লাস নাকি?
স্যার 12:30।
ঠিক আছে, তাড়াতাড়ি লেখো, তাড়াতাড়ি শেষ করো। হয়ে এসছে এটা। 12:30 থেকে কার ক্লাস? বিজেপি স্যার?
হ্যাঁ স্যার।
সরি। LP stands for low pass. হয়েছে? image rejection post filter, I have shown here the amplitude response, one-sided amplitude response. If you calculate from the frequency response, amplitude response of the zero order hold, you will find that at that frequency fs by 2, the zero order hold introduces an attenuation of about 4 dB. Now, image rejection filter, I pointed out, obviously, the cutoff frequency should be fs by 2. Therefore, it will introduce attenuation of another 3 dB there at fs by 2. All right. The image rejection filter doesn't improve the baseband distortion brought about by zero order hold. On the contrary, it also introduces some distortion, although very small. Why does this image rejection filter introduce this extra distortion? That is because the image rejection filter is a low pass filter. So for a practical low pass filter, analog filter, what happens? The gain is not constant over the pass band. The gain is drooping right from the value of f equal to 0. So that introduces some extra distortion. But for a well-designed post filter, this distortion will be minimal. capital G, CR, JF is the new frequency response of the new filter, second filter that we are bringing in. Compensated reconstruction filter. Sorry. একটু আমি এটাকে এনলার্জ করি, দাঁড়াও। So this filter, because we have assumed that the gain after fs by 2, it will be 0. So this filter can completely bring about a compensation. It can block the high frequency contaminants, and it can also compensate the effect of zero order hold, mutilating the baseband spectrum in the passband. All right. So both things can be done by this filter if it is possible to implement this filter. So that's why after the zero order hold, we are placing this compensated reconstruction analog filter. Necessity of that ordinary analog filter is no longer required if it is possible to place such a filter. Otherwise, simply a low pass filter in many applications it will do. But because that type of a characteristic GCR-JF in analog circuitry, it will be very, very difficult, if not impossible to attain. That's why I repeat, what is done is that prior to the DAC, some extra algorithm is placed, which will represent that type of a filter. So in majority of applications, this compensated reconstruction filter is not necessarily simply after the DAC, a post filter, a simple low pass filter with cutoff frequency fs by 2 that is placed, analog filter.
Sir, complete.
I have written down the expression for the frequency response. যে কোনো একটা লিখলেই হবে, GCR JF টা লেখো, J ওমেগাটা দরকার নেই আপাতত। Post filter means the simple analog filter with cutoff frequency fs by 2. We were there under a hypothetical situation that a certain analog signal, it was digitized. Then it was again converted back right after digitization to an analog signal to illustrate the errors introduced by a DAC and its remedy. But in actual signal processing system, obviously, after the digitization, there will be some processing by some signal processing algorithm. So Y hat T will be the processed signal, processed discrete time signal. So that can be converted to an analog signal YRT and then post filtered to yield Y0T, or you can place a compensated reconstruction filter prior to the DAC. XBT represents the band limited signal. The pre-filter or anti-alias filter prior to the ADC, it converts XT into a band limited signal, that is XBT. Run it. I think it's done.
Yes, sir.
So this is the last part. Now, because in this so-called digital equalizer prior to DAC, that will also not be able to attain that exactly this type of characteristic. There is a need for some post filter after this DAC, low pass filter. So that completes today's discussion. You have to take your lunch in this gap, isn't it? I don't know what you do.
Sir, complete.
Okay. So I am just logging out. You may leave if you wish.